And it's a pleasure for me that you are here, actually, because you are from a very important place. You do very, very interesting stuff that I don't understand, but I always found very, very interesting. So thank you for being back after a couple of years. Professor Marco LINARI from Florence, and he will present data about dual filament regulation of cardiac output. The stage is yours.
Thank you very much, especially for this kind invitation. The pressure in the ventricle is related to the nanoscale force at the level of the alt sarcomer, which is the functional unit of striated muscle. In the alt sarcomer, myosin motors are able to interact with the actin site, and this interaction is controlled by several regulatory proteins. In the classical view, calcium binds to troponin C and allow the exposure of myosin-binding sites on the thin filament. Myosin motors cannot interact with the actin site because they lie on the surface of the thick filament, and there is a mechanosensing mechanism that is clearly not completely known, which adapts the number of motors that leave this state and now they can interact with the actin sites. The aim of our research is to investigate mainly the off-to-on transition, and then in heart how the modulation of cardiac performance occurs by arterial pressure, which is the load for the heart. So how is possible to follow the state of the thick filament? In the X-ray pattern there are some reflections that mark the regulatory state of the thick filament. One of these reflections is the first myosin layer line, this reflection, which arises from the 43 nanometer three-stranded helix on the thick filament. With the myosin motors in the off state, the intensity of this reflection is high. Another reflection is the entry reflection, which is the third myosin meridional reflections, and this comes from the 43.3 nanometer axial periodicity on this axis, and at rest, and therefore with the heads in the off state, the intensity of this reflection is high, and this reflection shows a fine structure where there is one main peak and two small satellite peaks, low angle, high angle peaks. And those peaks are related to an interference effect of the two rays of myosin motors across the M line. Another reflection is the M6 reflection, and with the myosin motors in the off state, the spacing of this reflection is short. Other reflections are the forbidden reflections, the 1 and 2 and 4 and 5, and at rest the intensity of those reflections are high. Those reflections arise from a perturbation of the regular disposition of the myosin motors on the thick filament. In particular, the M5 reflection arises from a perturbation with a fundamental periodicity of 43 nanometer and a fine structure which is consistent with the localization of tightening in the thick filament. So the first point is just try to define how, if there are regional differences in the regulatory state of the thick filament. We perform the experiments at 27, 28 degrees, because in literature usually experiments are done at this temperature. The sample is an intratrabecular or a papillary muscle isolated from rat heart, and just to check the regulatory state, we use different temperatures. If we cool, if you reduce temperature, we have a reduction in the intensity of the first myosin layer line, but also of the entry reflection and of the interfering distance. This means that with cooling, we have removal of motors from the extremities of the thick filament. At 27 degrees, here is just the result of the model, structural model. One bar here means one myosin crown, one crown of myosin, so there are 49 crowns. At 27 degrees, we have some crowns which are not, some myosin which are not in the off state. And we can see that in the Z zone, all the heads are in the off state, but in the proximal and the distant zone, there are about 30% of heads that are off, that are on, so the thick filament is already activated. So the question is, does this preferential disorder in this peripheral region of the arthritic filament advantage these regions for the initial motor attachment? And to answer this question, we acquire X-ray data, the peak twitch force, and modulate the peak twitch force by changing extracellular calcium concentration or sarcomere length. And here are the results. Here we plot this reflection, the parameter of this reflection that mark the off state of the thick filament as function of the peak twitch force, the intensity of the first myosin layer line reduces, as well as the intensity of the M5 reflection. But the intensity of the M5 reflection drops more for the same force than the intensity of the first myosin layer line. This means that tightening is moving, and then there is the activation of the thick filament. The other reflection is the entry reflection, which shows this biphasic behavior as well as the interfering distance. And I will back in a moment on this reflection. Here there is the low angle peak of the entry reflection, which rises with the peak twitch force. This indicates or is proportional to the number of motors attaching to the acting filament. So in this way, we can say that there is a reduction in the motors in the off state, and the activation of the deep filament is complete for force larger than 40 kilopascal about, that the reduction of the motors in the off state is responsible also for the reduction of the intensity of the entry reflection, but then motors start to attach, and therefore the intensity of the entry reflection starts to rise again. The decrease of the motors in the off state start from the peripheral part, from the teeth zone of the thick filament, and then decreases, so just because the interference distance decreases, but then with the motor that attach, the interference distance starts to rise. So the attachment occurs from the central zone toward the periphery of the thick filament. We used a structural model just to explain, to global fitting the properties of the entry reflection, and here is a summary of this model. We have that the best fit of the entry parameters predict that the motor switching on spreads starting from the P and the teeth zone, and this activation is complete for forces of about 40 kilopascal. This is in agreement with the early tight immediate structural change as indicated by the intensity drop of the F5 reflection. The initial motor attachment for forces lower than 40 kilopascal occur in the seed zone. This is likely promoted by the myosin-binding protein C, which is located in that part of the thick filament. Further attachment for forces larger than 40 kilopascal occur from progressively more peripheral region of the thick filament, which is already fully on. And this could be related to the near network cooperative activation of the thick filament of the attachment motors. Next, we want to see how the dual filament regulation works in the modulation of cardiac output in more physiological conditions, and therefore using afterload contraction. And I finish here. I thank my collaborator and all of you for their attention. Thank you.
Thank you very much. Okay, do you have questions? How many of you usually are okay if they can catch when the muscle is on and off? Okay, now we can go to the next level and understand when the myosin is on or off.
No, just a clarification because I missed it. So, can you go back to the slide where you say which are the bridges that are recruited first? This one.
Yes.
So, because I remember it started from the other side.
On the other side.
Yeah, I had that in mind, so now I need to rethink of it.
This is a very nice question. Thank you. Because since there is a mechanosensing mechanism, the first idea is that if the first motor attached to the extremities, it works better because transmit the force all along the filament. And this is what we were thinking. And actually, at 27 degrees, so the temperature that we use, there is a disorder in the dead zone. And therefore, it would be really nice and easy to explain. But then, if you try to fit the parameters of the reflection, of course you need to structural model, and you get up with this condition, and I want to show you also other trials that we have done. For example, try to attach the motors all in uniform model of the active filament, or try to attach the motor at the extremities of the active filament. It didn't work, so it's not able to global fit in the properties of the reflection. So the solution that we found is this, where the motor attached first, and they are off, but attached first in the seed zone. We think probably data and literature showing that the noise invariant potency is able to interact both with actin and myosin, so could help in some way this interaction. Then, for forces we have here 40 kilopascal. This is an assumption of the model. We assume that when one head is attached per ground, so 1/6, the attachments start to spread. Just to explain this, the result that the interference distance increases. Because the interference distance increases, the attachment has to go toward the peripheral part of the filament. So this should be the description, let's say, of how the motors attach. The nice thing is that if you look to this figure, to this graph, here is the fraction of the heads in the off state in the three different regions. So you can calculate the average, and from the fraction of heads of all heads in the off state in the active filament, you can determine the intensity of the first myosin layer line, which is, let's say, explained quite well the experimental data. So the model has been done to explain the properties of the anti-reflection, but fit the intensity of the M1 reflection.
It's amazing because if you could see the surprise in the face of Professor Bottinelli, it means that it is normal that I understand nothing. But I'm very happy that you are surprised about it. We have no more time for other questions, but you can catch the myosin at the lunch. And thank you very much again.